Welcome to the earthquake and plate tectonic notes. Well, they're basically the earthquake notes, but you're going to find out that earthquakes and plate tectonics are tied together and there's a lot of connections between them. And without one, you're typically not going to get the other. And so I want to begin by just trying to see if you can figure out, how are earthquakes and plate tectonics related? What'd you come up with? Well, if you came up with the Earth is made of plates, and when these plates are moving, their interaction between the various plates cause earthquakes, you're correct. Now, when we start talking about earthquakes, the first thing I want to talk about is how many are there? You know, we don't usually hear about earthquakes every day in the news. You might see it only if there's a really large earthquake. You might see it in the news. But there's actually about 8,000 earthquakes a day. So if you average that out, that's about one every 11 seconds. However, the vast majority of these earthquakes we never feel. They're just too small. Only 1 in 5 earthquakes can be felt by people, and only 1 in 5,000 actually cause any serious damage. Now, between 1975 and 1995, there was a significant earthquake in every state except Florida, Iowa, North Dakota, and Wisconsin. And on average, Alaska has a magnitude 8 or greater earthquake every 14 years. It has had 12 7.0 earthquakes in the past 30 years alone. So when we look at the United States, obviously if you look at where we are in Wisconsin, right up here, if you don't know where Wisconsin is, we typically don't have a lot of earthquakes. Although last year there was, I think it was in Clintonville, they heard some mysterious booming, and some geologists are theorizing it could have been an earthquake. It could have been some plates shifting or some rock layers shifting that caused an earthquake. But it's not the traditional earthquake caused by two plates that have come in contact with each other and are interacting. So this is a seismic risk zone. So there are certain parts of the country, obviously here where you can see that it's red, they have a much, much higher probability of having an earthquake. But if you look around, there's some places, for example, down in southern Illinois, Missouri, Arkansas, Tennessee, Kentucky, in this area, they actually have a pretty good chance of having an earthquake, and that's the New Madrid fault zone. We'll talk a little bit more about that later. But even out east, a few years ago in Washington, D.C., in Virginia. So you're going to have earthquakes out here. You could have earthquakes in New York City, in Boston, in this area as well. So there's a significant chance of an earthquake happening in most areas. And while maybe it's unfortunate, but I think it's kind of good that Wisconsin's in an area where we don't really have much of a chance for earthquakes. So it's not one of those things you have to worry about. Now, an earthquake, what is it? It's basically any vibration of the earth caused by the sudden release of energy, usually as a result of faulting. But there's other ways you can get earthquakes happening as well. Now, major earthquakes are often followed by more, and these are usually smaller earthquakes called aftershocks. Now, I say usually. They technically do not have to be smaller. The aftershocks in some cases can actually be larger or at least equal in strength to the original earthquake. Now, what are some of the causes of earthquakes? 1, compression forces. Remember from our last unit, compression forces are created by convergent plate boundaries. These are where plates are coming together. Tension forces, if you remember from our last unit, this is where we had divergent boundaries. This is where plates are moving apart. And then we have shear forces. This is caused by a transform fault boundaries. And this is where plates are sliding past each other. And then what happens? Well, when rocks reach their elastic limit, they actually break and move, creating faults. Now, have you ever heard of the term elastic limits? You can test this out. Take a rubber band and put it in, stretch it between two hands and just keep stretching, stretching, stretching. That rubber band's going to have a lot of elasticity. It'll stretch and stretch and stretch. But once it reaches its elastic limit, it's actually going to snap. And it's hard to believe, but rock can do the same thing. It has the same capabilities as that rubber band. It will stretch and stretch and stretch, but pretty soon it's going to snap. And when that snapping happens, that's what we call faulting. And this is what causes earthquakes. So there are a couple different types of faults. First type of fault is a normal fault. Sometimes it's called a vertical fault, or sometimes it's called a dip-slip fault. So you might say, look at this and say, dip-slip? Why do they call it a dip-slip? Well, that's because one piece right over here will actually dip down, or in some cases they'll say it slips down. And that's why they call it a dip-slip fault. And so if you're reading a science book, a lot of times they call it a normal fault. But every once in a while you'll see it referred to as a vertical fault or a dip-slip fault. Now, where do we find these types of faults? One of the neat places where we can find these is on the Mid-Atlantic Ridge. Remember, this is where plates are moving apart. So at the Mid-Atlantic Ridge, maybe I should draw arrows this way, it's actually spreading apart. And this is created from tension zones. So these plates are pulling apart, and pretty soon rocks are going to reach their elastic limit and they're going to snap. So some good examples are the Sierra Nevada mountains in the western United States and the mid-ocean ridges. Now, a reverse fault is the opposite of a normal fault. Here, instead of this piece dipping or slipping down, it actually is thrust upwards, which is sometimes why they call it a thrust fault. So this is the opposite of a normal fault, which is why they call it a reverse fault. Where do we see a really good example of a reverse fault? Well, if you're looking over here, the Himalaya mountains. And these are created from compression forces. Remember, these two plates are coming together and they're being compressed. And Indian plate is being forced up and over the Eurasian plate. And this is why we get the Himalayan mountains. And this is why the Himalayan mountains are a good example of a reverse fault. Now, the last type of fault is the strike-slip fault. Sometimes this is called a horizontal fault. And the reason why it's called a horizontal fault is because it acts horizontally. This is where two plates are sliding past each other. And a really good example of this is the not Sierra Nevadas, but it's the San Andreas Fault. And the neat thing about it, and you can see it right here, it's coming down. And the neat thing about it is you got a shearing force, but it's on land. Usually these aren't on land that often. So it's a really good area for scientists and people to study strike-slip faults. So here you see it runs quite a ways through California. Goes right next to San Francisco. LA is on one side of it. So if you've ever driven out to places like Los Angeles, you've actually driven from one plate to another plate. You've got the North American plate and you got the Pacific plate. And here we see some of the faulting. So it's not, the San Andreas Fault is not just one clean fault, but there's all kinds of fragments and broken off pieces from it. And these are all different faults. And these are all capable of producing earthquakes. And here's a geologist studying it. So you can get in there, you can study it. I don't know if I'd want to be right there when an earthquake is happening, but you can do that. Here's a picture of a highway in California where you have all this cracking. This is kind of neat. If you look here, you can kind of see the shadow down there. There's probably a 2 or 3 foot drop. So if you can imagine this happening at night, imagine driving down the highway and it's pitch black. An earthquake happened maybe 20 minutes ago. You didn't feel it because you were in the car. And all of a sudden you're driving here and all of a sudden, woo, you're airborne until you hit. It's kind of like the Dukes of Hazzard. What would be worse if you're on this side and you hit, and if this side went up 2 or 3 feet, all of a sudden the front end of your car hits that. That wouldn't be so great. But yet you can see all this movement that took place, all this buckling that took place during the earthquake. Here you can see it running right through this ranch. So most earthquakes are the result of plates moving over, under, and or around each other. Most earthquakes in the United States occur out west. 80% of the world's earthquakes occur around the Pacific plate, and 10 to 15% occur around the Alpine belt. And I'll show you where the Alpine belt is. We mostly know the Pacific plate. You know, when we talk about volcanoes, it's called the Pacific Ring of Fire. And it basically outlines the Pacific plate. So when we look at the Pacific plate, here's your Pacific Ocean. And the Pacific Ocean basically outlines the Pacific plate, this whole thing right here. This is your Pacific plate. You've got other plates in here like the Nazca, the Caribbean plate in here. You got the Juan de Fuca plate, but you got the Filipino plate, but a large majority of it is the Pacific plate, and that's where a lot of the world's earthquakes occur. Now, I did mention the Alpine belt. That is in this area over here. It cuts through the Mediterranean. You can see it kind of on this side a little bit. Into Spain, Italy, Iran, into China. So a lot of the earthquakes that we see occurring in those places are occurring in the Alpine belt. So here's just a little different picture of all the earthquakes that have occurred. So again, you can see a large chunk of them occurring along the Pacific plate. But you also notice a lot of them occur along plate boundaries. Not all, but quite a bit of them. This right here is just going through some time, and it's just showing all the major earthquakes that are occurring. This actually took place in 2003, but it's just to show you that these earthquakes are occurring quite frequently. When we look at the United States, this is a map, and this was actually taken in 2002. I suppose I can look sometime, see if I can update this. But the whole idea here is just that a lot of earthquakes happen out west. And we also mentioned earlier, a lot happen in Wisconsin, but not all. Here's one that occurred, here's one that occurred. This is your New Madrid Fault. Remember, a couple of years we had one occurring in Oklahoma. So it's not something that's unheard of. They have occurred in Oklahoma. And that blue basically means it occurred in the last day. So it occurred right about when I snapped this picture off the internet. So what is seismology? Seismology is actually the study of earthquakes and the seismic waves that move through and around the earth. A seismologist is a scientist who studies earthquakes and seismic waves. So how do we measure these earthquakes? Well, they use something called a seismograph. And when we look at a seismograph, this would basically be a very basic model of what a seismograph would be like. Again, they're not going to actually look like this, but what happens is if the ground starts shaking, and this would be a weighted sphere, like a weighted ball, and if you look at Newton's laws of motion, one of the laws says that if things are at rest, they want to stay at rest. So this ball, even though the ground might be shaking and it's connected to this pole by the string, everything's shaking here, but this ball does not want to move. So what happens is the paper is going through, the paper is going back and forth because of the shaking of the earth, but because this ball is trying to stay still, you can actually get a reading of how much the earth is shaking. They'll use other things like laser distance ranging devices. Nowadays, we can use things like GPSs and satellites, and scientists can actually look at how far the earth is moving, in very, very small increments, where in the past it wasn't always easy to do. So here we see an example of what that might look like as it's moving. Here are some exact traces. So what you see happening here is that needle just goes through, and there's always a little vibration. All of a sudden, when it was coming through here, all of a sudden the earthquake happens, and then all of a sudden it starts jumping way up and down, because that's where it actually happened, the earthquake being. So here we see some different seismographs. Typically where you see the first wave right here, this is going to be your P wave. You've got your S wave, and usually there's some distance in between the P and S wave, and then eventually you have your surface waves occurring. So how do we figure out where an earthquake happened? Let's say an earthquake just happened. How do scientists figure out where it occurred? Where do we send aid? Well, it's actually something called triangulation. And it's pretty easy. If you have an earthquake happening, we don't know where it is. So here's Helena. What those people will do, they will know how far away the earthquake happened, but they don't know exactly where on that circle. But in Boise, they can also plot that, because they'll know how far away it occurred. They just don't know exactly where. And then if you're in Salt Lake City, if you plot it as well, eventually what's going to happen is where all three circles come together, that's where the earthquake happened. And that's called triangulation. Now, scientists will use a lot more than just three seismograph traces to figure out where it occurred. They'll use a lot more, so they'll know exactly where it occurred. But that gives you the general idea of how scientists can figure out where an earthquake occurred. So let's look a little bit more closely at these traces. So here's your background noise. Again, it's this coming here. Now, one of the first waves that's going to come through is a P wave, and it's just going to be a giant jolt. Then there might be a little space in between. And then all of a sudden you're going to get your S wave, and then finally your surface waves are going to be coming in. And we're actually going to be doing some of this in class where we're going to be working on triangulation. So you're going to get a lot better at this. And what scientists can do is when they know if a P wave comes in, say a P wave comes in right here. I will use this one right here. And then they can figure out how much later in time the S wave comes in. And they can actually look at that space in between them, and they can actually calculate the distance away from the earthquake's epicenter. Now, this does end part 1, and we are going to have the notes broken into a couple different parts. If you have any questions, as always, just ask your science teacher, and they'd be happy to answer any questions that you have. Thank you, and goodbye.